Okay, welcome everyone. This is the week 4 webinar, and hopefully you're all, plowing along with the class. And it's kind of a light week in terms of content, but there is your project that you should be, at this point, full blast, working on. So I would strongly recommend spending some significant time this week on the project so that you're ready to go and you'll have, feedback from me and all that, and get help from Braulio and all the different things. So that is pretty important. I want to give you a kind of, it's not for a couple of weeks, but a heads up. There's I'd say about a 20% chance that I will not make the webinar in 2 weeks because I may have to go to court. Any guess on why I may have to go to court? It's not for fun, but it's not as terrible as it sounds. Yeah, jury duty. Okay, and they usually cancel, but I got the letter in the mail. Just looked at today, and there it was. So it was during our webinar time. But again, they usually cancel. So let's hope that they, whoever is being convicted, negotiates and says, we don't need a jury. So just let you know that that'll be 2 weeks, and I won't know until unfortunately the last minute. So sorry about that. It's not something in that hopefully most of you are probably familiar with that you don't have any control on it. You get the letter in the mail and you got to go. So that's just a note, is I may have to go to court for jury duty. But if I don't, then and again, usually they cancel. About 80% of the time they cancel. So let me talk about the plan today. So the plan today is, as always, I'll answer any questions. And then we're moving to the most important distribution by far of any distribution we have in this class. I would say that on a scale from 1 to 10 on importance, the distributions we've had so far don't even reach a 4. Whereas we're going to be looking at the normal distribution, and a scale of 1 to 10, in terms of importance for statistics, it's a 10. Not A, it's the 10. It's the distribution. And next week, we'll see why. This week, you just got to trust the fact that it's important, because I'm telling you. And next week, we'll have the big theorem called the central limit theorem that basically says the normal distribution pretty much always happens if you do a survey right. So that's just a note. So we'll be looking at the standard normal distribution first. And that's when mean is 0 and standard deviation is 1, because that's the easiest of anything interesting. And then we'll talk about calculating probabilities and calculating percentiles when we have a normal distribution. And just let you know, it's very different than chapter 5. Chapter 5, we drew a rectangle, and then we did area equals base times height, and kind of worked it out that way. With normal distribution, you can't do it that way. And you can't just quickly find the area with some simple formula. I will let you know that I have a good guess that none of you would understand it if I told you how to do it, because it involves advanced calculus. So we're not going there. But instead, what I'll tell you how to do is how to use a calculator. And that you should know how to press the right buttons. And that's the important thing. We'll look at the general normal distribution also. And that is when we're going to be looking at maybe the mean could be something non-zero, like 50 or something. And maybe the standard deviation isn't 1, it might be 7. And how do you find out a probability and a percentile if you have a general normal distribution? And most normal distributions are general. The standard I'm just showing you because it's easiest to see what's going on. And you can use the standard to think about the general. Then we'll do an application or two. Okay. And it's one of those things where it's, we'll suppose it's a normal distribution. But again, next week, we'll see for any kind of, pretty much most every survey you do, it's going to have a normal distribution or a variation of a normal distribution. So that's how important this is. We'll be using it pretty much every single chapter for the rest of the course. will either be the normal distribution or be something that comes from the normal distribution. So it's an important one. So that is a plan. My guess is this will not take as long as the last few webinars because it's kind of a shorter chapter. But I like to talk about the syllabus because the big thing that's coming up in just a little less than 2 weeks, February 12th, is your project. So you should definitely be focusing on your project. And since we have a lighter week, then the project is a good idea. But it's also week 4. And 4 is a multiple of 2. Why is that important?
We got a quiz.
Yep. Yeah. I call it an exam, though. Yeah, to take it even more seriously. So 4 is a multiple of 2, and every multiple of 2 weeks, every even week, then you have your exam to take. So don't forget, just a note in terms of the exam, it has this very similar format to the exam you took week and a half ago or whatever for the week 2 exam, in that most of the problems are going to be just like your homeworks that you did, just like the chapter assignments. And then the last couple problems will be problems on where you have to type things out. Okay, you're given a box and you type it in the box, and then I grade those. So, and the last couple problems are weighted more heavily than the others. The ones I grade are weighted more heavily, so take them seriously. Don't leave them blank for sure. So that is important. Also, it's week 3 and 4 is weighted more heavily in terms of the number of questions you're going to get than week 1 and 2. So the new stuff always has more problems than the old stuff. There is old stuff though, so it does cover everything. Okay, and that's how all the exams will be, is they'll cover everything, but they'll highlight the newer stuff. Any questions at all about the project, the exams, anything else about statistics? Any questions?
I have a question.
Sure.
With the graph that we need to be plugging in, or the spreadsheet that we need to be plugging in our information, you have like numbers on the first on the first page of it. And I was curious if those are just examples and we delete those and put in our data, or
I figured I'd share it. It'll be easier to see. So I'm opening up as we go.
Like the 32.
Yeah. So I put those numbers in, and they're different numbers every week because I'll throw in a number just for fun now. 44. So that you see that that's where numbers go. But when you do your project, after you've made a copy, the next step is going to be highlight and then backspace, and that deletes them all.
Okay.
And then put your numbers in.
Okay. Okay, perfect.
Okay, I'm putting them back in because it's good to have numbers there. Yeah, don't use my numbers because that's not what your numbers are. Does it make sense?
Yeah, and then all the tabs below where it says like regression, chi-square, we use all of those too for our project?
No.
Okay, good.
No. So, but I will tell you, you don't have to worry about this for a while. This 2 VerStats, that'll be project 2.
Okay.
So you will use
on this page.
Yeah, you will use the second tab for project 2. And just a note, again, you never need it, but everything that we do in our class, all the calculator stuff, I've been showing you the other calculator, can be done with this also. And that's one of the reasons why I put all of these guys in. Does that make sense?
Okay.
But you don't have to use any of those, because since I made this, I created an easier calculator, which you'll see again today because I use it all the time. But a lot of people do use all of these from other classes from all over the country. So I'm not going to get rid of them because other people are, other classes from other places are using it. And also, if in the future, and I mean your future, not this class, you need to use like something with many, many data values, then the calculator that we use in class won't work. Does that make sense? So if you, for your job or something, need to use 100 data values, then our course then what I've been showing you in the class doesn't work because it only has kind of a limited number, always enough for any homework problem or anything like that, but not enough for some real life stuff. Does that make sense?
Yeah.
Whereas
Okay.
this will work for anything real life.
Okay.
Yeah. Anything that has elementary stats doesn't have advanced stats in it.
Okay, sweet. Thank you.
But yeah, good question. Good question. Okay, other questions? Let me go back to our week 4. There we go. Any other questions? Okay, so if there's no questions, what I'll do now is talk about the standard normal distribution. And I've already mentioned the normal distribution just briefly. Do you remember the shape of the normal distribution in a word or two? Possibly one word. It came up a few times.
Bell shape?
Yeah, it's a bell curve. You've all heard the bell curve. It turns out there's lots of different names for the normal distribution. One is a bell curve, and that's like the simplest name. What we're going to be using in our class, and you need to use, is a normal distribution. Okay, and then the third thing that you might hear sometimes here and there is the Gaussian distribution. And that's the guy who created it. His last name was Gauss. So, you know, you might hear it in different places with different words. But in our class, we'll use normal distribution. We'll always use the word normal. It's easier to stick with a specific one. So let me show you a picture that's really important. This is the picture of the standard normal distribution. And hopefully you can all see it. And hopefully you agree, it kind of looks like a bell. Not perfect, but yeah, bellish. Okay, and that's, again, the shape of the standard normal distribution. Okay, as I mentioned a little earlier, when it's a standard normal distribution, the mean is 0, because that's the easiest mean you can have in terms of calculations and stuff. So notice that the normal distribution is symmetric and unimodal, which means that the mean and the mode are going to be the same, because when you have a symmetric distribution, then the mean and the mode will be the same. And unimodal will tell you it's right at that mean, and that's 0. Okay, so that's important. So the standard normal distribution will always have its mean and mode and median all at 0. Then there are these numbers: 68%, 95%, and 99.7%. And we can say 68% of the data is between -1 and 1. 95% of the data are between -2 and 2. And about 99.7% of the data are between -3 and 3. And this is rounded to, like, you know, as many decimal places as you're looking at right now. Just let you know, it's really like 95 point something, but, but 95 is what everyone remembers. Do you remember we had a rule for that earlier that was important? What was the name of that rule? That was that 68, 95, 99.7. It happened, I know it was a couple weeks ago. Maybe 3 weeks ago. It was at the very beginning.
Quartiles?
Yeah, good. I got it in the chat box. Empirical rule. That was the empirical rule. So the empirical rule, if you remember, said if you have something that is a normal distribution, we use the word approximately normal. Then, and if it's approximately normal, then it's approximately 68% for 1 standard deviation, approximately 95% for 2 standard deviations, and approximately 99.7% for 3 standard deviations. That was the empirical rule. And because that was done at the very beginning of class, of the course, make sure that if you have a normal distribution in your project, after looking at your histogram, then you should use the empirical rule, okay, and apply it. Okay, if you don't have something that looks like a normal distribution, so if you have a distribution that's like, say, highly skewed left, or maybe it's bimodal instead of unimodal, then you can't use the empirical rule. And then you have to resort to like plan B, which is not nearly as good. And that's called Chebyshev's theorem. Okay, that's just a note for your project. Okay, and if you don't remember that stuff, you can always look it up. It's there in the book, and we talked about it. But the empirical rule is really important for this week because we're doing the normal distribution. Okay, any questions about this picture? Okay, I'll let you know that the uniform distribution had a, it was really easy. Base times height, right, was the area. If you had to find the area of some randomly thing, or show it was 68% or 0.68 here, good luck. Good luck. You're not going to be able to do it unless you've had a huge amount of mathematics. Okay. So it's not like a uniform distribution where it's just simple base times height and you find the area. Here, the area under the curve is very intense and involves some very high level calculus. So if you've had beginning calculus, that's not even enough, because you just can't even use like the first semester or first couple quarters of calculus and get this to work. Just let you know that. And if you haven't had calculus, you don't have no clue. So just let you know that that's not going to happen. But what is going to happen is we can always say this and we can use it. Okay, so let's do some examples. Okay, so the first example is find the probability that if I randomly select an item that is coming from a normal distribution, that is a standard normal distribution, that item will be somewhere between -1 and 1. And the answer to this is really easy. So what's the answer? What's the probability that you get something between -1 and 1?
68%.
Yeah, 68% or 0.68. Okay, because that comes right from the empirical rule. Any questions on that? Was that easy? It was supposed to be. Okay, now we're going to get a little harder. Okay, what if we wanted to find out, we're going to randomly select an item that is coming from a normal distribution, a standard normal distribution. And let's find out the probability that that item will be less than 3. Okay, so the probability, if I'm going to use the letter Z, that Z is less than 3. That's harder. Okay, and the reason why it's harder is if you look at this, less than 3 is from here, where 3 is, all the way out here, forever and ever and ever and ever. We know between 3 and -3, but less than 3 is not one of these guys. So any thoughts on how we might do this? Okay, and I don't expect you guys to all get it, but let me show you. And the way to do it is use symmetry. So the idea is the probability that Z is less than 3. This is a symmetric distribution, which means less than 3 is all of these guys. So if I can find greater than 3, then I can find less than 3 by using the rule of complements. Remember, the rule of complements says that less than 3 will be 1 minus greater than 3 for a probability, right? Because if there's a certain percent chance of being less than 3, there's 100% minus that percent of being greater than 3, right? That's the rule of complements. So what we can say now is this is 1, so I got the equality, equals 1 minus the probability that Z is greater than 3. Any questions? Any questions on that? Okay. So now we got to find out what's the probability that z is greater than 3, and that's still a problem because we only know between -3 and 3. So what we're going to do is we're going to use symmetry. So being greater than 3 is this part right here. But we can go to the other side and saying being less than -3 is over here. And if we combine those two, that's going to give us twice as much as being greater than 3. So what we can do is we can say that's equal to 1 minus 1/2, because if we get something twice as much, we get to divide by 2, times, and now we got to find the probability that we're either less than -3 or greater than 3. But if being between -3 and 3 has a 99.7% chance, so if being like in this area has a 99.7% chance, then being outside the area is going to be 1 minus that. More rule of complements. So it's going to be times 1 minus, and that's 0.997. Any questions on that idea? Okay, and then the rest is basic arithmetic. So that's equal to, I don't know, 1 minus, I'll let you do it. But hopefully y'all know how to put that in a calculator. I could do it in my head, but it's because 1 minus 0.997 is 0.003. A half of that is 0.0015. 1 minus that, 9985. Stick it in a calculator. Any questions on that idea? Okay, so now let's do the third idea. And that is, let's find the probability that z is between -1 and 2. So the problem with this one is we know the probability between -1 and 1. We can know the probability between -2 and 2, but these are different numbers, -1 to 2. But again, we can use some basic, geometry just by looking at pictures and saying, well, to be between -1 and 2. Let's see what that is. Well, that's the same as between -2 and 2. So we can say between -1 and 2 is what? Well, that is what? That's between -1 and 1 plus 1 to 2. Do you see that? Because if I take this piece, this middle piece here, -1 to 1, and I add in this piece 1 to 2, I get -1 to 2. So I can write that's the probability that -1 is less than z is less than 1, plus the probability that 1 is less than z is less than 2. Any questions on how I added those two pieces together to say that it equals the same piece? The nice thing about area is you can do that. You cut the area into two pieces, you add the two areas up, and that gives you the original area. Okay, so now probability between z is -1 to 1. That's easy, because we already answered that. That was 0.68, empirical rule. Any questions on that? Plus, now we have to go -1 to 2. But how do we get -1 to 2? I'm sorry, 1 to 2. How do we get 1 to 2? Okay, the idea is you do the same thing that we just did before, is use symmetry. 1 to 2 is going to be half of -2 to -1 plus 1 to 2. Okay. But if I take this piece plus this piece, that's going to be -2 to 2 minus -1 to 1. So I can write 1 over 2, that's the half. And then I can take -2 to 2, and probability -2 to 2 is 0.95. And the probability that we're between -1 and 1 is 0.65, 68. 68%. Any questions on that? Okay, and I don't think I'm gonna, deal with how to put in a calculator, I hope, at this point. Okay, you do it by hand if you felt like it, but you don't have to. Okay, so now let's do the next one. Find the value of Z such that there's a 2.5% probability of being greater than this value of Z. All right, so the idea here is the first thing is Z going to be kind of on the left or kind of on the right? If there's a 2.5% chance of being bigger than that number. It can be left side or right side. Think about this way. If 2.5% of the people are taller than you, are you tall or are you short? That's kind of the same idea. If 2.5% of everyone is taller than you, are you tall or short?
Short.
Okay, 2.5%. If 2.5% are taller than you, then don't forget that tells you what 97.5% are shorter than you. If almost everyone's shorter than you, are you short or tall?
You're tall.
You're tall. If very few people are taller than you, you're tall, right? If 2.5%, that's a very small percent, are taller, then you're tall. Does that make sense? So similarly, if we want to find the value of Z such that only 2.5% are bigger than the value of Z, the value of Z is going to be out here somewhere, going to be on the right, high side, like tall side. Okay, so now what we can do, so, we don't know exactly where Z, it could be here, or here, or here, or somewhere in the middle. But what we can say is that if 2.5% are bigger than that value, if we use symmetry and go to the other side, 2.5% will be smaller than the symmetric other side. What's 2.5% plus 2.5%? Hopefully you all know 5%, right? So 5% are on the outside. How much is in the inside? Yeah. So if 5% are on the outside, 95% are on the inside. So now we just look up here, 95% goes from -2 to 2, but we're on the right-hand side, so it's 2. And that's your answer. Z is 2. And that's it. There's like nothing to do other than kind of see it. Because 2.5% on the high side, 2.5% on the low side. So that means 5% extreme, 95% in the middle. 95% goes from -2 to 2. So we're on the high side, so it must be 2. Any questions on the reasoning? So it's logic that we're using, right? Very little heavy math. It's just logic. Any questions on that? Okay, I think I'm going to go to this next one. Is if Z is 1.3, find the Z-score for the standard normal distribution. If Z is 1.3, find the Z score. Do you all remember the formula for the Z score?
X minus mu over standard deviation.
X minus mu over sigma over standard deviation. So because it's got a fraction, let's stick an equation in. So Z is equal to, make a fraction. And our X in this case, or our Z is 1.3. Okay, and actually, let's make it bigger. It's hard to see, I think, for you guys. There we go. Okay, so 1.3 minus, what's the mean of the standard normal distribution? 0 over the standard deviation. What's the standard deviation of the standard normal distribution? I've said it a few times. Yeah, it's 1. So now comes some very easy math. Hopefully you don't need a calculator. What's 1.3 minus 0 divided by 1? The hint is very easy. What's 1.3 minus 0 divided by 1? Yeah, it's just 1.3. 1.3 minus 0 is 1.3. 1.3 divided by 1 is 1.3. So the Z-score for the value 1.3 is 1.3. And by the way, if I gave you a different number instead of 1.3, like, I don't know, negative 0.7, you get negative 0.7. And that's the reason why throughout all of these things, I use the letter Z for the variable. Because when you have a standard normal distribution, then the value of the variable is its own Z-score. Because if you subtract 0 and divide by 1, you don't change the number. So that's kind of a nice property for a standard normal distribution. Any questions on that? Okay, and by the way, if you remember, this is important for your project. When did we say something was an outlier? What was a kind of our class's definition? Yeah, when the Z-score is more than 2 or less than negative 2, right? Okay, well, if Z is more than 2 or less than negative 2, and we have a normal distribution, then there's only a 5% chance of that happening. And that's kind of the standard for deciding when you have an outlier. If it's a very rare chance, less than 5%, we call it an outlier. And if we use negative 3 to 3 for extreme outlier, because that's like 0.3% chance, that's like really rare. Any questions on that idea? So to decide whether something's an outlier, you find its Z-score. Okay, if you have a standard normal distribution, you don't do anything. But if you have something else, then you got to find the Z-score. Any questions at all on the standard normal distribution before I move on? Okay, so now comes the next one. Let's suppose now we don't have a standard normal distribution. Now we have just a general normal distribution. And let's suppose the mean is 114. Let's make this bigger so you can see it. Let's say the mean is 114 and the standard deviation is 23. So it's not standard anymore. Okay, first thing is, and it's kind of similar to what we did with uniform in terms of notation. We're going to use X now because it's not a Z-score, because it doesn't have a 0 mean and 1 standard deviation. And then if you remember that tilde means has the distribution. What do you think N stands for? It's not a trick question, by the way. What's N stand for?
Is it normal distribution?
Yeah. Yeah. So tilde means has a distribution that is normal. And then 114, the first number is the mean. 23, the second number is a standard deviation. And that's the notation we're going to use to talk about a normal distribution. Okay. Okay. And by the way, it's a curve. We saw, there's a curve. Do you think there's a math equation that gives you this curve, or this one or whatever? And the answer is yes. And the good news for you guys, it's brutal. Why is that good news?
We won't have to do it, maybe.
Yeah, you're not responsible. You're not responsible for brutal stuff. But I'll say it really fast. X minus, it's going to be it's 1 over the square root of pi times e to the negative x minus mu quantity squared over sigma squared. So don't worry about it. Okay, so again, you don't have to worry about it. So we're going to do it differently. So we're going to find the probability that x is between 100 and 120. Okay, so again, you have a normal distribution. You can draw a curve. You can go from 100 to 120. Notice 114 is somewhere in between there, right? Okay. How do you think we might find this probability? Given that I told you it was brutal in terms of the equation.
A calculator.
Yeah. And this should be obvious, I hope. Which calculator do you think we're going to use?
The normal probability.
Yeah, normal probability. Okay, I did my best to make it obvious. Okay, there are no tricklings here. So I got normal probability. And it's going to ask you the low, the high, kind of like the binomial where you had the low and the high. Do you remember that? There's not number of trials, though. It's not binomial. There's a mean, there's a standard deviation, and there's a probability. And the way you do it is you put in all the ones you know, and one of them you leave blank. Does that make sense? So if you put in all the ones you know and you leave one blank, it'll give you the blank one. So in the example that we wanted to look at, we want the probability that x is between 100 and 120. So it should be easy. What's the low?
100.
And the high is?
120.
And the mean was 114 and the standard deviation was 23. So I got 114. Standard deviation was 23. That wasn't too hard, was it? And I hit calculate. And that's what I get. By the way, this down over here, this is like a note in case you screw up somewhere. Think it's like if you leave two blank, or there's just certain things that could happen. There's one case where you get two answers and it gives you that. So I just grab one. Okay. You're never going to need this many decimal places, by the way. So, sometimes you'll need 4 decimal places if it's in the, computer graded stuff, 0.3315. So however many decimal places you need is what it is, 0.3315 in this case. Any questions on that? Okay, so the next one, probably that x is greater than 200, and this is a little tricky. So first thing is we don't know the probability, so I'm going to leave that blank. The mean and standard deviation are the same. We want to be greater than 200. What's the low for greater than 200?
200.
Yeah, 200. So just to note, this is a continuous distribution, so don't put 201. With a continuous distribution, you could have 200.000000001. Do you see? And that would still be greater than 200. So that needs to be 200. What's the high if you're greater than 200?
A bunch of 9s.
Yeah, technically it's infinity, right? So technically the high is infinity, but infinity is not really a number. Does that make sense? Okay, infinity is not a number. It's just a word. So we're gonna like kind of trick the computer. And what I do is I look at all the numbers here and I say, which one has the most number of digits? And if it's a tie, it's fine. How many digits are there for the most number of digits?
3.
3 digits. So for the high, I'm going to take 3 and I'm going to add 2. And that's 5. And I'll put 5 nines. Okay, so the idea of a bunch of nines is great, but I want to be more specific. You want to do 2 more nines than the highest number of digits that are in the list. Does that make sense? So, and that will work. And the reason why it really works is it sends it so many standard deviations above that after that, it doesn't matter. The probability is like lower than any decimal places you'd ever be able to get. And then I hit calculate. Okay, so not a very big chance, not 0, 0.000. Let's go 4 decimal places. So to 4 decimal places, what is the probability? Yeah, 0.0001. So don't forget rounding. So you go to that 4th decimal place, you look at the one to the right, that's a 9, which is 5 or bigger. So that means you round up. So 0.0001. Any questions on that? Okay. Now we're going to find the probability that we're less than 90. Okay, so again, we don't know the probability. We want to be less than 90. Okay, mean and standard deviation are the same. We're using the same distribution. So now we need the low and the high. And what can we do for less than 90? What do you think the low is going to be if you're less than 90?
-5 nines.
Yeah, exactly. Because it's negative infinity, and we're going to use the same rule, is go the maximum number of digits, which is 3, add 2 more, that's 5, 5 nines, but it's on the negative side. So it's negative 1, 2, 3, 4, 5. Okay. And by the way, if you use more than 5, that's fine. It's just more typing. But you better have at least 2 more than the number of digits, and then you're always good. What's the high for less than 90? Yeah, 90, because it's a continuous distribution. So that includes 89.9999, you know. Okay, and that stuff can happen. You can get something really close like that. Okay, and in fact, for example, to win an election, what % of the vote must you get?
$51.
Okay, I'm glad you said that, because then I can explain why that's not right. Okay, the rule is you have to get more than 50%. So let me give you my own personal experience. My first election that I ran for, I was on the ballot. I ended up getting 50.002%. I didn't get 51%. I got 50.002%. Did I win?
Yes.
Yes, I won. Yeah, I won. That was my first term. Second term, I got 94% of the vote. And so that was an easy one. First term was a very hard election. And so just know that greater than 50% doesn't mean you have to be 51%. It can mean 50.0001 or something. So that's why we can set, in this case, less than 90, we can set 90 as the high, and it's safe because there's so close to 90, that's good enough. Okay, don't put 89, in other words. Okay, and then calculate. And again, if we go 4 decimals, that's what the computer usually asks for, 0.1484. Okay, the next one. Find the probability that X is greater than 105. How do I read this little thing here? What's the word for that? Yeah, given. Given X is less than 125. So if I want to do that, I need to use chapter 3. Because chapter 3 is when we learned about given. Remember that? And there was a formula for given. And that was the same thing as the probability of both of these happening. Now, X is greater than 105 and X is less than 125 is the same as 105 is less than X, which is less than 125. That's the and. So then you divide by what's given, and that's X is less than 125. And that was a formula from chapter 3 as a probability of A given B is the probability of A and B divided by the probability of B. And if you don't remember it, that's fine, but you should have it in a place that you can easily find it if you need it. That given formula, because it's an important formula. Any questions on this example so far? So now we actually need to do two things. We need to find the numerator's probability. We need to find the denominator's probability. So the numerator, 105 to 125. Very simple with the calculator. 105 is a low. 125 is a high. We don't know the probability, so we leave it blank. And I calculate it. Okay. And I get, if I round to 4 decimals, 0.33. Actually, usually you don't want to round until the very end. So I'm going to copy and paste this guy. And then I'm going to divide by the probability that we're less than 125. So now, being less than 125, what's the low? It'd be less than 125. What's the low? Wouldn't be too hard. But we've done one like it already. Yeah, negative 9999999. So negative and 5 ninths. And we want to be less than 125, right? So I'll keep that 125 there. Empty the probability. And we get this big number. And it's this division. I can actually literally just copy this sucker. We can go scientific calculator. And I can paste it in. And you get about 0.4914. Any questions at all on that example? Okay, so the next question is find the IQR. Do you remember what the IQR means? What's it stand for? Let's start there.
Interquartile range.
Yeah, it's the interquartile range. And then there's a formula for it. How do you find the interquartile range? Do you remember?
Subtract Q3 from Q1.
You get the idea. You subtract Q1 from Q3. That's maybe what was in your head, though. So it's Q3 minus Q1. Because the big minus the small. Any questions on that? So you go Q3 minus Q1. So now let's go back here. And we want to go Q3. Q3, what is that? What does that stand for?
%, 0.75.
Yeah, so that means there's a probability of 75% of being less than that value. So we know the probability this time, it's 0.75. What we don't know is the value. That's the high. So to be less than that value, you go between negative 99999 to high, which we don't know, and we're going to leave the high blank. Any questions on that? And then very simple, I hit calculate. And I get, I'll just go for decimals, 129.5133. Minus, and now we want to do Q1. And the good news is, it's the same idea, but instead of 0.75, what do we use?
0.25.
0.25. And again, everything else is the same. We don't know the high. Let's find the high. And it's 98.4867. And we can pop that in the calculator. And you get 31.0266. $31.0266. Any questions at all on finding the IQR? Okay. So by the way, watching me is not the same thing as really knowing how to do it. So make sure, you do lots of practice so that you can get the hang of it, especially before the exam, because you're gonna have to do some of this stuff probably. Okay, the middle 84% of the data is between what two values? That one's gonna take a little bit of thinking. Okay, so the middle 84% is between what two values? It might help, oops. Get some blank space in here. It might help for me to draw a picture. So let's do that. And that's going to be one of these buttons. Annotate, there we go. Okay, so that's the picture, normal curve. And we want the middle 84%. So that's going to be like something like here to here. Any questions on that? And what we want is we want to find out what those two values are. This is 0.84. Let me make that point a little darker. Is that clear? So this is 0.84. Okay. What's this area here? How do I get that? And here's the idea. And this is kind of what we had to do from the earlier stuff. If 84% is inside, how much is outside? Yeah, 16% is outside. If 16% is outside and there's symmetry, how much is on the left? Yeah, 8%. So this right here is 0.08. Any questions on that? Okay. And this is the first value that we don't know yet, right? So let's go find it. And that's the good news, is that's not so hard anymore. So we now can say that the low is going to be negative 99999. The high is what we don't know. The probability is 0.08. And we're in the same problem, so it's the same mean and standard deviation. So now I can go to, let me unannotate because I gotta, did that do it? Yeah. It still shows up a little bit. So the low is a bunch of 9s. The high we don't know, right? And the probability is 0.08. And we calculate, and you get 81.6834. Rounded to 4 decimal places. That's the left value. Similar for the right value. If this is 8%, then this is also 8% over here, right? So we're going to do the same idea, but now the low is what we don't know. The high will be a bunch of 9s. And now we got to find the low. And when we do that, it gives you 146.3166. Any questions on how I came up with the middle, the two values that have the middle 84%? Any questions on that? Okay, again, the warning is it's always easier to watch than to do. So when you have to do it yourself, it's a lot harder than watching me do it. But I figure I should do one like this because you may be asked to do one too, because some of the exercises are like that. Okay, which means some of the exam problems could be like that too. Okay, how about the z-score for the value of x equals 117? So that's actually quite easy because we have a formula for the z-score. It's x, which is 117, minus the mean. The mean was 114. Divided by the standard deviation. Standard deviation was 23. And I'll let you put that in the calculator. Any questions on finding that z-score? Not too bad? Okay, so again, I can't emphasize strongly enough how important the normal distribution is. I'm going to do some applications now. And let me erase this. Let's find out how to do that. Annotate. Text, stamp, spotlight, eraser. Let's see. Clear. There we go. Got it. Good. And then just a minute. Try a few things. That one. There we go. So I like this example. It's kind of a neat example. And I think that I know there's a few of you that are going into healthcare. And this is the one part of healthcare where the people who come are glad most of them are glad they have this health issue. Any guess what it is? But people come to the doctor and are happy that they have this health issue, where most people are happy. Nobody's guessing? Because you can have a baby. And so here is an example. Okay. So suppose the time until you or your wife, if you're male, will give birth is normally distributed with mean 140 days and standard deviation 7 days. By the way, if mean is 140 days and you want to talk to just general people who don't like statistics, what do you say?
Average.
Not average, that's still statistics. What's the word everyone uses for being pregnant? the question people ask. When are you expecting?
Most common,
Yeah, no, when are you expecting? Right? When you say, when are you expecting? And then someone answers, I'm expecting in 140 days, that's the mean. Does that make sense? When the doctor says, when we're expecting the baby, that's the mean. Does that make sense? That's standard. Okay. And the standard deviation is 7 days. That used to be true for humans, by the way, not quite true anymore. You don't know why? And if you're in medical, you might know. If you're not, you still might know, but you know, in medical, you eventually better know. Should I tell you? C-sections. Yeah, so if we're looking at babies that are born, living babies that are born naturally, then the standard deviation really is 7 days. Okay, C-sections changed everything. Okay, so that's what we've got. Okay, and by the way, I'll let you know that's what my brother does for a living. He gives birth. He delivers babies for a living. Not gives birth, sorry. He helps women who are giving birth. So he's a baby deliverer. It's kind of cool, isn't it? Okay, so so I know a little bit about it. So the first thing is I can write down this. This is the way to write down this normal. This announces that we have a normal distribution. This announces that the mean is 140. This announces that the standard deviation is 7. Any questions on the notation? All right, so, okay, here's the question. Again, this is hypothetical. Okay, your boss has just scheduled you or your wife, okay, for a business trip to China. Okay, and it may not be true. I'm going to assume that you're American. Okay, you're living in America. Okay, and your boss say, no, you got to go to China. Okay, you or your wife leave today and will return in 135 days. Find the probability your baby will be born in China. Okay, because this stuff's important, isn't it, to understand? Well, what do we have to do? How do you find this probability? Well, we want to find the probability to be born in China. That means that the baby was born before we returned. Does that make sense? Because if the baby's born after we return, then it's born in America. Again, we're assuming you're in America. So that's the same thing as find the probability that X is less than 135. Because you're returning in 135 days. So once you know how to do it, it's easy. If you refresh, it clears everything, by the way, just let you know on the calculator. So what's the low?
-9,999, maybe.
Yeah, -9,999. Yeah, and we should take a look, make sure this is a 3-digit number. This is a 3-digit number. We don't have any more, so 5 nines is enough. Okay, so low is -9,999. Okay, and yeah, you can't really have a baby in -9,999 days, but this is hypothetical normal distribution. If you use 0, you get the same answer, it turns out, but we're not going to do that. Okay, what's the high? Again, we want the probability that we're less than 135. What's the high? It's not a trick question. 135. What's the mean? 140, and the standard deviation is 7. Any questions on that? And let's calculate. And my guess is that you're happy enough to 2 decimal places to turn into percent, right? So it looks like about a 24% chance. Okay, do you think you'd be okay with that if you're pregnant or if your wife is pregnant? If there's a 24% chance that she's going to be like out of the country and going to deliver the baby outside of where you live. Do you think that's okay? Yeah, I hope you say no, by the way, if you want to stay married, by the way. Yeah, that's not okay. Okay, so you're going to say no. No, you're going to tell your boss, forget it, right? Does that make sense? But you don't want to just quit. So you're going to negotiate. And that's part B. Okay, so you decide it's too risky. And you negotiate with the boss to ensure that there's no more than a 1% chance. Okay, so you'll be okay at a 1% chance because that's very unlikely. Does that make sense? Okay, and you want to negotiate. So, what day should you ask your boss to be the return date? Does that make sense? So if we only want it to be a 1% chance, then what date should we ask the boss for the return date? So the idea here is 1%. Where does a 1% go? Yeah, that's the P, and we need to turn to a decimal. And now it's the high that we're negotiating, so that's what we're going to leave blank. And if I calculate, probably round it to the, and you're negotiating, so I'd probably round to 123. Because we want it to be less than 1%, not greater than 1%. So 123 would probably be the negotiating date. They're going to return on after 123 days. Any questions on that? And then if you return after 123 days, then you have less than a 1% chance of having the baby in China. Any questions on that idea? Okay, so now we're going to jump up a bit, jump forward. It's now 138 days later. Okay. It's 138 days later. Remember that we're expecting at 140 days. So we're 2 days for expecting date now, right? So it's 138 days later, and the baby still has not been born. Find the probability that the baby will be born within the next 24 hours. Any questions on the question? So the idea is we know now the baby hasn't been born. What kind of question is this going to be now in one word?
Is it given?
Yeah, this is a given because we're given that we're greater than 138. Do you see how that works? So we want the probability. And by the way, if it's born in the next 24 hours, that means it's born between day 138 and day 139. Because right now we're at day 138. In 24 hours, we'll be at day 139. So we can go 138 is less than X is less than 139, given X is greater than 138. Any questions on that idea? Okay, do you remember we did a given problem already today? What did we do?
The probability of both of them divided by the probability of B.
Yeah.
X is
Yeah.
greater than B. Yeah.
Yeah. So notice that if it's between 138 and 139 and it's bigger than 138, that's the same thing as being between 138 and 139, right? Does that make sense? So if I tell you that I'm between 50 and 60 years old, and I'm older than 50, what do you know? I'm between 50 and 60, right? The second thing didn't tell you anything new. So what we can do is we can just find the probability that 138 is less than X is less than 139. And then divide by, because that has that and in it, it has the greater than 138 anyway. Divide by the probability that X is greater than 138. So 138 to 139, go back to the calculator and we just plug them in. 138, 139. We don't know the probability. And there we go. That is this messy thing. I'll just copy paste it. I love copying and paste. So easy. Okay. And then the probability that we're greater than 138, well, that starts at 138. Where does it end?
One 138.
138 to 138 would be a 0 probability, by the way. That means you're like exactly that moment.
Oh, 140?
No, greater than 138. What's the biggest
Oh,
number
so-
greater than 138?
Mm.
5 nines.
Yeah, 5 nines. Okay. Does that make sense? So greater than 138 has no upper bound. You just put a bunch of nines in. Same mean standard deviation, get a new probability. Let's calculate. And you get this number. So let's put it in. And then go copy and paste again. I'm going to pop it into the scientific calculator. And you get about 9% chance. Any questions on that? Okay, so, that's getting to be a higher percent chance, which means probably want to stay pretty close to the hospital. Any questions on that idea? Okay, let's do one more example. And there's an ice cream example. So suppose that the amount of ice cream that you sell, so you got an ice cream store, sound good? And the amount of ice cream that you sell every day is normally distributed. And let's suppose the mean is 950 ounces and the standard deviation is 120 ounces. Okay. So X is normal with mean 950, standard deviation 120. Find the probability that on a randomly selected day, you'll sell between 900 and 1,000 ounces of ice cream. So do you understand how that works? So we go over here. We're on a new problem, so I'm just going to refresh. It's easier. And again, we want to be probability we're 900 to 1,000. So low is 900. High is 1,000. The mean was 950. Standard deviation was 120. And that's it. We hit part P. About a 32% chance. Okay. 0.3231 if you want 4 decimals. 3231. If I went too fast, let me know. But basically, these problems are, hopefully they're all looking similar, do they? So hopefully you're able to kind of follow along and you'll be able to do your own because there's only so many kinds of problems you can do. That's the good news. Okay. In the morning, you took stock of your supplies and you noticed that you have 1,100 ounces of ice cream in your store. Okay. What's the probability that you'll run out by the end of the day? Okay. So to run out means that that people are going to want to buy more than 1,100 ounces. That makes you run out. Does that make sense? Okay. And these are important, by the way, if you own a business, you got to think about this stuff. Because if you're running out, especially if you own an ice cream store, and someone comes to your store and you say, oh, sorry, we're out of ice cream at our ice cream store. They're never going to come back again. They're going to tell all their friends to never come back, and you're going to go out of business. Does that make sense? So you don't want to be out of ice cream often. You better hope there's a low probability. Is that clear? So if it's not a low probability, then you probably need to have more ounces of ice cream. You better grab some from somewhere. So let's go find the probability that X is greater than 1,100. What's the low? $1,100. What's the high? Yeah, in this case, we need 6 nines. Because we already have 4 digits for this low. Do you see that? So you should use 6 nines. We don't know the probability, so we leave that one blank. And we calculate. What do you think? As a business person, would you be okay with this? If there's over a 10% chance you're going to turn customers away and tell them sorry? Yeah, probably not. So you probably need to go and get some more ice cream, however that can be done. Okay, so the probability is about, 0.1056. All right, so similarly, if you want to be 99% certain, okay, that you will not run out of ice cream, how much do you need to have in stock at the beginning of the day? Any questions on the idea? So here we're given the probability is 0.99. We need to find out what X is. So let's go up to the calculator. Our probability is 0.99. Okay, I want to make sure 99% chance we don't run out. So what are we looking for now? We're not looking for the low this time because, again, if we go from the low to infinity, that's the running out area. We want to not run out. Do you see? So we want to go from like basically 0, okay, or negative 99999 to our how much we need to get. So we're going to let this one be negative 99999. And the high is what we don't know. And we want to make sure that so then there's a 99% chance that we're between no one comes for ice cream and whatever this value is. Do you see how that works? That's what we want to be that's what we want to be most likely. And if I click that, it's 1229.1617. So have 1,229.1617 ounces in stock. Any questions on this idea? Did I lose any of you? Okay, so it seems like these are the main examples, but these are not the main examples. I want to give you a heads up. Okay, the main examples will come next week. Just let you know. It turns out the main examples come from sampling. Okay. There are things that have a normal distribution that aren't samples, but most don't, but samples do. Let me tell you, there's something that you've known probably since you were even maybe less than 1 year old. that has a normal distribution? And you knew it by looking at it? Something you probably really liked doing when you were a kid and maybe still like doing, probably still like doing. Going to the beach. And you drop some sand in a pile. What's the shape? You've all seen it, right? It's a normal distribution. It's a normal curve. Okay, it's a three-dimensional normal shape curve. But if you cut it into just a shadow, it's a normal curve. Can you all picture that? If you can't, then you really should go to the beach. Because that means you don't go to the beach often enough. And it's too much fun, especially in summer. So it turns out that there's a reason for that being a normal distribution, and that we're going to cover next week too. Lots and lots and lots of things have normal distributions, but it's all because of this next week's stuff called the central limit theorem. And what I'm going to do now is what's left, which is perfect. The secret word. It's tricky. It's not a word. It's a number. The secret word is 95. Do you know why? There aren't 95 people here, by the way.
95%.
Yeah, because the empirical rule says if you have a normal distribution, then there's 95% of the data lies within one standard deviation of the mean. So 95 is the secret word, put in quotes because it's really a secret number, but I like to do that. So hopefully, again, we're finishing a little earlier than usual because a little less talk about, and again, you should really be, think about your project. I do want to, is there anyone here that, let me stop the share and stuff, but I want to stop the recording. That one.